Our next topic is angle. So we'll be able to define the angle between two vectors. It's gonna be the same as the angle between vectors that have dimension 2 and 3, but we're going to be able to talk about things like the angle between two vectors of dimension 1,000, which is a very interesting concept. So we're going to start with something called the Cauchy-Schwartz inequality, and it's named for two mathematicians, Koshi and Schwartz. And it says this. It says, if I have any two n vectors, a and b, then the inner product, the absolute value of the inner product, is less than or equal to the product of the norms. That's here. And so if you write it out in terms of coefficients, it says this. It says that the absolute value of the sum of the corresponding products, that's the inner product, is less than, that's the norm of A, and that's times the norm of B. And if you have, once you have the triangle, and once you have the Cauchy-Schwartz inequality, you can establish the triangle inequality. And let's see how that works. They're related. A plus B norm squared is equal to, and I'm simply going to multiply everything out because that's A plus B inner product with A plus B, and that's equal to the inner product of A with itself plus the inner product of A with B plus the other way around, and then plus that, okay? This is norm A squared, that's right here. This term is right there, and then these two are both a number, and they're the same number. It's the inner product of A and B, or B and A. It's the same number, and so that goes in this middle one. So I've derived that first line. Now I'm going to use the Cauchy-Schwartz inequality in the middle thing, 2 inner product of A and B, and I'm going to say that that is less than or equal to 2 times the norm of A times B, and I get this, but that's exactly equal to that. And now I take the square root of this, and I find that A plus B, the norm of that is less than or equal to the norm of A plus the norm of B, and that's the triangle inequality. So once we know the Cauchy-Schwartz inequality, we can actually show the triangle inequality from that. So let's derive the Cauchy-Schwartz inequality. This is also something where, it's probably best for you to derive this yourself and in your own terms and things like that. But we'll just do it here because it's not that hard to do. So first of all, the Cauchy-Schwartz inequality is clearly true if either A or B is 0, because then both the left and right-hand side will be 0, right? Because you'll have the inner product of any vector with 0 is 0. That's the left-hand side. And on the right-hand side, you'd have one of the terms would be the norm of a 0 vector, okay? So we can assume that both A and B are non-zero, and that means that their norms, and we'll call those alpha and beta, are positive. So these are positive numbers. Now what we're going to do is we're going to simply do this. We're going to say that 0 is less than or equal to, and what we're going to do is write out, it's a particular linear combination of A and B. It's kind of weird, actually. It's just basically, it's the norm of B times A minus the norm of A times B. That's a linear combination. And we're going to expand out the norm squared of this difference, and we get something that looks like this. It's the norm squared of the first term, norm squared of the last term, minus twice the inner product of the two terms. And so that's going to be this thing here. We're going to rearrange a couple of things. Like here, the beta will come out, and it becomes out as beta squared. Here, alpha comes out as alpha squared. I'm using properties of the norm there. And then here, using some properties of the inner product, the alpha and beta come out in front, and you get something like this, right? So in this case, we get this expression here. And what we get is that that's the same as this thing. Is we get 2 times the norm squared of A, norm squared of B, minus 2 times norm A, norm B. Here what I've done is I've used the fact that alpha is the norm of A and beta here is the norm of B. And when you plug those back in, you get this thing. And what we know is that that thing is bigger than or equal to 0. This first one applies immediately because a norm is bigger than 0, norm squared is bigger than 0. So that's how you get that. Now, if you simply divide that by this, you get Cauchy-Schwartz inequality. And you can also apply it to minus A and B, and you get the other half of the Cauchy-Schwartz inequality. So that's the Cauchy-Schwartz inequality. I have to admit, this is what we call a mystery proof. Because you look at it and you'd say, where on earth who would think of writing down the norm squared of this bizarre linear combination here? And that's okay. There's lots of other ways to derive the Cauchy-Schwarz inequality. This is just one of those. So I'm just saying I would not have expected you to do this, but I've done it for you. So that's fine. Okay. Now that we have the Cauchy-Schwarz inequality, we can actually talk about angle. And the reason, let me explain how that goes. It says that the ratio, if you have two non-zero vectors, then the ratio of A transpose B to norm of A norm B, now we know by Cauchy-Schwarz that's a number between -1 and +1. Can't be any outside that range. Well, that means that we can actually take the arc cosine, and that means that we can actually take we can simply we can associate an angle with that, and we're going to literally define that to be the angle between the two vectors A and B. Okay, so that's how that's going to work. And it's going to be a number between 0 and pi, or if you prefer degrees, this is radians, 0 and 180 degrees. And it's the one that's going to satisfy this, that the inner product is norm A, norm B times the cosine of the angle between A and B. Now, turns out this is exactly the angle in 2 dimensions and 3 that you knew about in maybe an analytic algebra or analytic geometry course. It is exactly the same as the angle, right? If I say what's the angle between these two vectors, you would get exactly this formula. What's interesting for us is that the formula works, and we associate angles between vectors of dimension 1,000, right? So, which is sort of interesting. We'll get to that. By the way, the angle is another kind of measure of deviation between two vectors, right? If the angle is 2 degrees, it means, roughly speaking, the vectors are pointing kind of in the same direction. If it's 90 degrees, not so much, and the most they could disagree with each other would be to point in 180 degrees apart from each other. But we'll get to that in a minute. Okay, so people classify angles. These are very useful to know about. So I'm going to take theta. That's a traditional symbol to denote an angle. Is the angle between 2 non-zero vectors A and B. So if theta is pi over 2, that means that A and B are orthogonal. And people write it this way. You write A with this little upside down thing, which suggests 90 degrees, right? A is orthogonal to B. And it's just a very fancy way of saying that the two vectors have an inner product of 0. It means nothing more. If theta is 0, that means that A and B are aligned. So let me first give you an example visually. So here's an example of orthogonal vectors, right? So the blue and the red vectors are orthogonal. They have an angle of 90 degrees with respect to each other. Aligned means that the inner product takes on the largest value you could possibly take given the norms, and it's norm A times norm B. And that occurs when basically, roughly speaking, they point in the same direction. That's what it means. It means the angle between them is 0. If theta is 180 degrees, or pi radians, right, that means they're anti-aligned. And that would be this picture here. It says that they're actually on a line, but they point in exact opposite directions. So that's anti-aligned. If the angle is less than 90 degrees, then that says that the inner product is non-negative. And we say that they make an acute angle. And the converse, well, not the converse, but if it's bigger than 90 degrees, we say it's an obtuse angle. So here's an example. These two vectors make an acute angle. I don't know what the angle is between them, 25 degrees or something, but it's acute. And the inner product is non-negative in that case, positive. In this case, the angle is more than 90 degrees. I don't know, 110, 100 degrees. I don't know, some 105 degrees. Anyway, so this would be an example of two vectors that make an obtuse angle. So, and these are just completely standard concepts in all of math. So this is what you're going to see. Okay. Another application is spherical distance. So here, if I have a sphere of radius r, and A and B are on the sphere, so this is supposed to be a point on the surface, and that's a point on the surface, then I can talk about this, right? So the distance between A and B, that's this thing. That is the distance, but that's the distance of, basically, if this was the Earth and these are two places, of drilling a hole directly from one through the Earth to the other. And that would give you this number here. Okay? The distance along the sphere says you have to, what's the shortest path from one to the other, but you have to stay on the surface of the sphere. Okay, so no drilling. If you do that, it turns out that's exactly equal to the radius times the angle. The angle in radians, of course, not in degrees. That gives you spherical distance. So that's another way to think of angle as giving you some kind of a spherical distance, right? So that's kind of the idea. The last thing we're going to talk about in this section is that you can use a document you can measure things like document dissimilarity or feature distance using angles, and people do that. And so a lot of times people will say, oh, how are you measuring the feature distance? And they might say, oh, by angles, right? Or by distance, right? Euclidean distance. But let's look at an example. We're going to look at the same one we looked at last time, a previous example. And what we do is we have 5 Wikipedia pages, one Veterans Day, Memorial Day, Academy Awards, Golden Globe Awards, Super Bowl. And for each of those, we're going to work out a vector, which is the word count vector with a dictionary of around 4,500 words, right? So we just do that. And then what we do is we're going to calculate the angles between pairs of these things. Now, whenever you ask what's the angle between a vector and itself, it's always 0. So the diagonals are all 0 here. Let's see. Let's look at the angle between Veterans Day and, so you could ask again, which two of these feature vectors, the feature vectors are nothing but word count vectors, which two have the smallest angle? So which ones are closest together in an angle, right? And so once again, the winner is Veterans Day and Memorial Day. So by that, it's suggesting that somehow of these five Wikipedia pages, these are the two closest. Now, they are literally the closest as measured by angle in feature space, right? But the interesting thing is it picks up on some stuff. And you would probably, if I went to a person on the street and said, here's five Wikipedia pages, which would you consider to be the two that are closest? You'd probably pick these two. But you might pick Academy Awards and Golden Globe Awards. Oh, yes, indeed you might, because guess what? That's actually the closest one. My apologies, okay? But they're close, and that gives you a rough idea. Interestingly, you see things like this. Golden Globe Awards and Super Bowl are off by 86 degrees. Now, the inner product of two word count vectors are non-negative, and the inner product of two non-negative vectors, non-negative vector means a vector that's all of whose entries are non-negative. The inner product of two such vectors is, of course, non-negative, and that means that all of these angles had to be acute. They have to be between 0 and 90 degrees. So what's interesting about this 86 degrees, is it's saying that they're pretty far apart. They're about as far apart as they could possibly be, 90 being the only other choice, or that's the biggest they could possibly be. By the way, I should add that for word count vectors, if the angle is 90 degrees, turns out it means that the two documents share 0 words in common. In other words, that for every single word in that dictionary, either it's not in one document or it's not in the other. You could look at that, or we'll make a homework problem on it to have you work that out and figure out what it means. Anyway, so once again, this is a hint that looking at just angles can actually have practical applications. Next topic is the so-called correlation coefficient. Again, this is something you'll see in other courses, I'm pretty sure, or may already have seen in a basic probability course. Here we're defining it in the context of, well, vectors, right? So what we do is we take two vectors A and B, we demean them, so I get A tilde and B tilde. I should add that this is not universal mathematics notation, so it's my local notation. So don't go to the math department and say A tilde and they go, what are you talking about? And you can't say it's the demean vector. They would say, well, I didn't know that. So just so you know, I mean, you can write this, the inner product, and that everyone will recognize, but not the tildes. So just so you know. Okay, so we demean these vectors, And the correlation coefficient is defined. It's used. This is that is kind of a standard mathematical symbol for correlation. Rho, the Greek character letter rho, and it's equal to the inner product of the d-meaned vectors divided by the product of the norms. Now, if you took the arc cosine of this, you would get the angle between the d-mean vectors. Okay, so here what this means is, if rho rho is literally the cosine of the angle between them. So rho equals 0 means that they're uncorrelated, and it means A tilde and B tilde are orthogonal, right? That they have 0 inner product. If rho is bigger than about 0.8 or so, it depends on the application, you would say that A and B are highly correlated. If it's less than minus 0.8, you'd say they're highly anti-correlated. Now, you might ask, what does this correlation coefficient mean? And what it means is actually super interesting. It means the following. You take these AIs and BIs, and you ask questions like, when are they above their average? Like, for what I's are they above their average? And when are they below their average? And if that has nothing to do with each other, and sometimes, A is above its average and B is below, and sometimes, that kind of thing, then they're going to be approximately uncorrelated. If, however, they're correlated, what that tells you, they're highly correlated. What that says is very often when A is above its average, so is B. That it's more or less at the same time, roughly, that they're above their averages. So that's roughly the idea here. So here's an example. We've got 3 examples of pairs of vectors, which we've plotted just for your eye to follow it. Here's A, here's B. And in this first one, you take a look at it. I don't know what the mean is, but I'd say it's about there. And I don't know what the mean of this is, but it's not too different like that. And now, again, let's use my intuitive idea of what correlation is. You could see that, it's over here in index like 2, 3, 4, whatever, roughly, that A is above its mean. And sure enough, B is above its mean, maybe not in the first one, but in 2, 3, 4, 5, something like that. And also similarly, A is below its mean here, and so is B. And sure enough, these are very highly correlated. And if I do a scatter plot of A against B, what it says is they kind of fall on a line. That's what it means to have perfect correlation. So they fall on a line like this. Okay. Our second example is here's A. Here's B, and again, I don't know what the mean might be, somewhere around here. And here, they're anti-correlated because you can see when A goes high, B goes low. High means above its mean, and B goes low. And as a result, when I scatter plot A versus B, they're on this declining line like this. And that means they're anti-correlated. And here, sure enough, they're highly anti-correlated. And here's an example where when you do a scatter plot of A and B, they're just kind of all over the map. And you can see here, A is above its mean sometimes, so is B, but all 4 things happen, I'm being very rough here, but approximately the same, right? With same frequencies, sometimes A is above, B is below, sometimes A is above, B is above, and all 4 possibilities you get. So that's it. Oh, I should add that things like correlation is also defined in basic probability. And in fact, this corresponds precisely to that in a certain setting. But here I'm just talking about for vectors. So okay, so here are some examples, practical examples of highly correlated vectors. Here you go. How about the daily rainfall time series in Palo Alto and Menlo Park? There you go. These are adjacent cities. Okay, so honestly, they're very close. So these would be highly correlated, right? That in the summer in California, you basically don't have any rain at all. When it's raining in Palo Alto, it's probably raining in Menlo Park, this kind of thing. So that would be an example of highly correlated vectors. It would be like 10 years of daily rainfall data. That would be a 3,650 vector long. Okay. Here's another one, maybe not as highly correlated, is daily returns of similar companies in the same industry. So let's look at, let's say, a year's worth of returns. There's about 250 trading days in a year, so that's about 250 numbers. So if I look at, 2 similar companies and I look at their returns, They will be, if the companies are similar, meaning they've got about the same capitalization, they kind of are in the same industry or something like that. Of course, the returns are not going to be the same, but they're going to be pretty correlated because some of the same things are driving both of them, right? Some of the same underlying causes. And so that's the idea. Correlation is not going to be 95%, but it could easily be 0.8 or something like that. Here's another one. Word count vectors of closely related documents are going to be highly correlated. So that's that's an example, right? So for example, things written by the same author or things on the same topic, right? So these are going to be fairly correlated, right? Okay. Here's another one. It's a classic one from economics. It's kind of silly, but it's the sale, maybe a time series of sales, let's say weekly sales of shoes and socks. You know, and those are going to be, those could be at different locations or different periods. And then the point is, those are correlated because basically when people are buying shoes, they're probably also buying socks. I mean, so you know, are they exactly the same? Of course not. But you know, you would see that they were highly correlated. So examples of some approximately uncorrelated vectors is just two vectors that are unrelated, right? So an example would be go get the daily maximum temperature in Bordeaux for 10 years, and I have a 3650 vector. Okay, there it is. It varies, right? It's cool in the winter and you know, high in the summer. I don't know. Okay, and I go and I get let's say the rainfall in the Amazon forest. Actually, I should be careful because those probably would have some correlation with seasonality. But I could actually just go get some other vector of the same length, and then it could be simply this. It could be the weekly purchases at a company of 3,650 different products, right? So the point is they have nothing to do with each other. And quite likely they are going to be essentially uncorrelated. A practical example of this is audio signals, right? So when audio signals are encoded as vectors of length, which is about 44,000 per second. So even a 10-second clip is pretty big. It's 441,000 actually long. And if I just take two audio clips that are each about 10 seconds long, they're going to be approximately uncorrelated. I mean, almost very, very closely. I mean, unless they were two microphones recorded, within, half an inch of each other or something, in which case the correlation coefficient might creep up. But other than that, they're going to be completely uncorrelated. I mean, approximately. Okay. So if you want to look for some negatively correlated vectors, daily temperatures in Palo Alto and Melbourne. Okay, why? Because one's in the northern hemisphere, one's in the southern hemisphere, and kind of when it's above the mean yearly temperature in Palo Alto, it's because it's summer, and that's exactly winter in Melbourne. So that would be an example of that. So these are just some examples to give you the flavor of what it means to be correlated.